Hello again, you're hanging with Hussick. This video is going to talk about isomers. This is organic compounds that have the same molecular formula, but either some difference in the bonds connected between the atoms or some difference in the permanent arrangement of some of those bonded groups within the molecule. So the prefix iso is really important because iso means same. So the same molecular formula, but slightly different arrangement. Okay, so as I just suggested, isomers are molecules with the same molecular formula, okay, same molecular formula, meaning the same number of each type of atom, but they have different arrangements of those atoms. And so what it results in is that we have entirely different compounds with entirely different names and different physical and chemical properties. Okay, so for example, the molecular formula, let's go to blue here. The molecular formula might be C4H10, okay? But what we see is that there are different forms of C4H10. So I'm just going to draw the most linear and basic. And this is an alkane, since all the carbons have single bonds. And this would be called butane. Okay, it's a 4-carbon alkane. Whereas if I mix up, again with an alkane, but I mix up the arrangement of the carbons a little bit, and I tack one on carbon 2 as a methyl group, now it's not butane anymore, but we would call this 2-methyl propane, because the longest chain is 3 carbons, okay? And if you compare butane to 2-methyl propane, you'd have some similarities, like they're both alkanes, they're both nonpolar, etc., etc. But obviously, what we also see from their different names is they have some different physical and chemical properties. Butane, because it's linear, would end up having a higher melting point and boiling point because it's more stackable. We talked about this a little bit with intermolecular forces, but when they're more linear, they can stack on top of each other more often and more easily and have more interaction, so they have stronger dispersion force. Whereas 2-methyl propane is a bit more branched, a bit more spherical, so it would have a slightly lower melting point and boiling point. You could look this up and confirm that I'm right. Okay, so chemically, they could react different as well. And we don't see major differences with alkanes, but with some compounds, like if we look at carboxylic acids a little bit later on, you could see that depending on which way those functional groups are organized and arranged in the molecule, it can make a big difference in the way they react. So in terms of isomers on a whole, these two are what we would call structural isomers because they literally have different sets of connections in the way the carbons are bonded together. There's 3 types of isomers, and we're going to look at those 3 types of isomers now. So the first type of isomers are called structural isomers. Same as the example I just showed you with 2-methyl propane and butane. We see that the bonding is actually different. So if you count, the way the molecules are arranged, you'll see there's a totally different bonding scheme. For example, with C3H6, we could have it bonded together in a cyclic like this. Okay. And I'll even put the hydrogens in here so you can count them up and prove that I'm not pulling your leg. Okay, so you could have it bonded like that. Or, and you may recognize this from the formula because it's in the form of CnH2n, isn't it? And if you remember, that's the general formula for an alkene. So actually we can also show this as an alkene like this. Okay, a 3-carbon alkene. If you fill out all of the hydrogens, you're going to see that there's 6 of them. Okay, so it's following the same molecular formula, C3H6. But now instead of being, what would we call this? We'd call this cyclopropane. Okay, A-N-E because it's all single bonds. Cyclo because it's a cyclic. Instead of cyclopropane, now we have propene over here. Propene or 1-propene or prop-1-ene however you like it. These would be structural isomers. And for some molecular formulas, there are many, many different structural isomers that exist. And this is one thing that we can kind of have a fun time, if you find it fun, we can have a fun time playing the game of trying to determine the structures of all different structural isomers, or as many as we can for a certain formula. Okay, the second category of isomers are called stereoisomers. And we're not going to dwell on these a lot because it can become really complex. But stereoisomers occur when a carbon central atom, okay? So a carbon bonds to 4 different groups. If this occurs, the mirror image of the compound with this carbon in it is a different molecule than the original. Okay, so we sometimes refer to a carbon, in this case, the one that I've highlighted in yellow here. We sometimes refer to this carbon as a chiral carbon. Chiral, or the prefix, I don't know, prefix chi, like a chimera. It means it's many different things. And so chiral suggests it bonds to many different things. Well, what happens is the mirror image of that compound will be an entirely different compound. Sometimes this is referred to as handedness. Okay, so it's like handedness. It's like the way your left hand and your right hand, they're similar in structure. You might even say that they are the same in structure, but in reality, that you can't put a left-handed, it kind of looks like he's giving the finger. That wasn't my intent, but whatever. Kind of looks like, as you can see here, they're mirror images. You can't put a left-handed glove on your right hand, and you can't put a right-handed glove on your left hand. Or maybe it manifests a little bit more clearly with shoes. You can't put a left-footed shoe on your right foot. You can't put a right-footed shoe on your left foot. However, in both of these structures, it's like a palm is bonding to a thumb and to fingers. Palm, thumb, fingers. Like, the bonding isn't different, but actually we can tell there's some subtle difference in the molecules. And if I show a proper molecular example here, it would be like if you have a carbon bonded to 4 different things. So let me just put 4 different things around it. A fluorine, a methyl group, an iodine, and a bromine, okay? And then imagine we held up a mirror, okay? So we had the iodine here, and the fluorine here, and the bromine here, and the CH3 here, okay? What you would find if you put your eye at the position of the methyl, okay, and looked, you would see from right to left it would rotate iodine, then fluorine, then bromine, and so on, right? If you did the same this way, it would go fluorine, iodine, bromine, fluorine. So the rotation would be slightly different, and the way that those reacted with other molecules would be really different. And there have been some examples throughout history where they're called enantiomers, the different enantiomers, or the different of these compounds, the 2 different versions of these compounds, react really differently in a very significant way in biological systems. Okay, so we won't talk much more about stereoisomerism until you get to university if you continue doing organic chemistry there. But just beware, this is the second form, or one type of isomer that can exist. The third form of isomerism is an important one for us, and we're going to spend some time on this, and that is the cis-trans isomers. So what we see in cis-trans isomers is the use of the prefix cis when the larger groups are on the same side of a molecule, and the use of the term trans when the larger groups are on opposite sides of the molecule. Okay, so this occurs in molecules with restricted rotation. Okay, when there is restricted rotation, and we'll talk about what that means in a minute. What that essentially means, okay, is that you've got a carbon-carbon double bond present in the molecule, or you've got some sort of a ring structure present in the molecule, okay? What does this have to do with rotation? Well, if you have a carbon-carbon single bond, the way we understand it, and actually if you think back to our unit on bonding, we said that really what happens when you have a carbon-carbon single bond is you've got an overlap of orbitals, okay? So you've got these orbitals that overlap like this. And since they overlap like this carbon can rotate all it wants, and this carbon can rotate all it wants. So essentially, in the end, you have free rotation around any carbon-carbon single bond. So just think of it like it can spin around. Well, as soon as you have a double bond involved, or a ring structure, they're not free to spin anymore. They're restricted. They're locked is another way to think about this. They are locked in place, okay? So when that's the case, depending on what side chains or branches or substituents are there, you can have cis-trans isomerism. I'll show you with a few examples. So if you have a look at this model of a representative molecule here with a double bond providing restricted rotation, you see I've used some notation R1 and R2, R3 and R4, okay? So when we use the term R, we can say that we actually call them R groups, and R groups just means something bonded on to the carbon, okay? So something or some chain or some alkyl group, some branch, whatever. It's something bonded onto the carbon, okay? So if we look at these R groups and we see that R1 is not the same as R2. In other words, you have two different things on that side. And over here, R3 is not the same as R4. Then this is the condition where cis-trans isomerism will exist. Cis-trans isomerism exists. Okay? If you have the case where across that double bond R1 or R2 are the same, okay, so if R1 is equal to R2 and R3 is equal to R4, like it's an OR, okay? So this was an AND scenario. This is an OR scenario. So maybe I can write that a little bit more clearly here for you. So if you have that OR, R3 is equal to R4, then there is no cis-trans isomerism. Okay, so now let me get to that example where I can show you. Okay, I'm going to show you with examples a couple different ways the cis and trans form cis and trans isomers of a molecule. So here we have a molecule, and if we highlight like we did before those R groups, you see that that is not the same as this, and you see that this is not the same as that. Okay, so we have the condition for cis-trans isomerism. What we should also notice then is that if you look at the heavier of those substituents on each side, okay, so that's going to be the chlorine. If you look at where it is, it's pointing in, and this chlorine is pointing in too. So they're on the same side. They form kind of like a letter C, and we call this the cis form of this compound. So this would be called cis. Now what's the actual compound called? You can see it's got two carbons. It's a 2-carbon alkene. So it is going to be called ethene. And then of course we have to assign the chlorides, the chloride residues. So it's a cis 1,2-dichloroethene, okay? Compare that to the trans version. So if when this molecule is made by whatever process it's produced, either by a plant or in another living system or in a lab, whatever, if this isomer is spat out instead, okay, you'll see that there's the chlorine on this side and then the chlorine's on that side for this one. So it looks more like a chair. Sometimes they call this the, what do they do? They call this the boat, okay? And they call this the chair. I don't know if you see that or not. It's a bit like a chaise lounge or something. But this would be called trans 1,2-dichloro ethene, sorry. Okay, so you can see that really all the bonds are the same. It's a carbon on each side bonded to a chlorine and a hydrogen and another carbon, but the arrangement in three-dimensional space where those substituents are locked is slightly different, and so this is how you get cis and trans isomers. Show you a couple more. Before I get too far into the weeds on that, you should realize that this would not have cis. This would be no cis trans, right? Because look at what's on each carbon. You have actually R1 is equal to R2, as we were saying. So this is not cis trans. This would just be called 1,1-dichloroethene. Okay, so if they're on the same carbon like this, you know, it doesn't matter how that carbon is rotated, whether it's locked in this position or it's locked in the other position, it's going to be the same molecule. Okay, whereas you look at these two that I just wrote here in blue, and you analyze the R1 and R2, R3 and R4 on each side. So have a look here. That one's not the same as that one, and that one's not the same as that one. Okay, on both of them. And so this does exhibit cis-trans isomerism. So now what we do is we name the molecule carefully, and then we assign which is cis and which is trans, okay? And so if you look at this one and you say, remember your naming rules, what's the longest run of carbons? It's actually 4, okay? See, it's 1, 2, 3, 4. So this is going to be a bute, right? And then we see it's got the carbon-carbon double bond after carbon 2. So it's going to be but-2-ene, we could say, or 2-butene. And so this is the type of but-2-ene where the heaviest substituents, this one and that one, are on opposite sides. So this would be referred to as trans but-2-ene or trans 2-butene, as opposed to this guy over here where both of the heaviest as they appear side chains, even though they're really a part of the parent chain, aren't they? Those are on the same side. So this is the cis version. This would be called cis, I'll write it the other way, cis 2-butene. Okay, so you're looking for a double bond or you're looking for a ring structure. There's some other resources on looking at ring structures on this. Okay, so we have to practice drawing isomers. So I might give you a question that says, draw all isomers of C4H8, okay? How do you approach this? Well, like I said earlier, you may realize this is CnH2n, which tells you that it's an alkene, or at least one of its isomers will be an alkene. So we can go ahead and make an alkene. Yeah, why not? And then let's put in the hydrogens and see if we got to 8. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So we know that's one of the isomers. What else can we do? Well, we can slide that double bond around, right? We can put it over here. Then we add our hydrogens and count. Yep, we got to 8. That's also one of the isomers, okay? We could realize then that if we have put that double bond in the middle, if I actually redraw this one, so I'm going to draw the exact same compound. This isn't a separate compound, but on that same carbon, so see that's the same carbon there, I'm going to show that the hydrogen's up there and the methyl's down there, and on this one the methyl's up there. Even though it's not a methyl, it's actually part of the same group, but you get what I'm saying. And lo and behold, look at this. We have the trans isomer, right? So we have the trans version of this, and a completely different isomer is the cis version. So we'll show the cis version where they're on the same side. Okay. So we've got the cis version. So we have the trans and the cis. Those would count as separate isomers. And then one thing you don't want to forget is try some ring structures. So we can put a ring structure together. Let's just put all 4 of the carbons in a ring and fill them up with hydrogens. Does it work? Sure it does. There's another one. Okay, so that's going to be C4H8 as well. And what about a 3-carbon ring? Does that work? I don't know. Let's see what happens. We put 3 in there. We need another carbon out there. Fill out the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. My God, we got another one. Okay, so this is the game. I don't know if you find it fun. It can be a little bit fun and satisfying, to be honest. If you find it fun, great. If you don't find it fun, you've got to do it anyways, because I'm your chemistry teacher and I'm saying you have to. But you can explore different types of isomers this way, and just always explore, like, can I make a ring like this? Can I make a ring like that? Maybe even a bow tie style ring. Okay, that wasn't, I'll draw one of those to show you what I mean. A bow tie style, like where there's a carbon in the middle here and carbons out there on the edges. Okay, try everything. There's another one here where we could have had both of these, I don't know if I'm supposed to call them methyl groups, would-be methyl groups, on the same carbon over there too. And if you look, that's the other isomer of C4H8. So in the end, we've actually got 6 different isomers here, right? We've got 1, 2, 3, 4, 5, 6. Okay, so I could ask you to do this. I could ask you to draw 6 or draw 8 or draw 10 isomers of a certain molecular formula. Okay, so I'll show you another one. Okay, so I could say draw 5 isomers of C4H9. Now, actually I want this to be, I wrote the wrong thing. C4H6, okay? Now again, you'd look at this and God knows how many isomers there actually are. Turns out there's 9 apparently. I don't know this off the top of my head or anything, but I'm looking at a paper that has it on. So there's 9 different ones, but I'd ask you to come up with 4 or 5. One thing you should realize again is if you look at the general formula, this looks like a CnH2n minus 2, doesn't it? Okay, so you may recognize that means an alkyne is at least one of the forms. So let's try and come up with that alkyne. Let's put all 4 out there and say, yeah, how about that? 1, 2, 3, 4, 5. No more room for hydrogen on that one. 6. Okay, so that's definitely 1. What if we move that triple bond to this position here? Does that work? 1, 2, 3, 4, 5, 6. Yep, there's another one. Okay, so things like this. Again, try ring structures. They tend to be fantastic. And every time you put a ring in, you kind of reduce, like you take away a triple bond and put a double bond in the ring is kind of how it works. Okay, so you try a structure like that. 1, 2, 3, 4, 5, 6 hydrogens. There we go. You could try a 3-member ring. Put a double bond in there. 1, 2, 3, 4. Oh, we don't have enough carbons. Here we go. That's probably why. 1, 2, 3, 4, 5, 6. Okay, there's one there. You could try sliding that methyl group around to different carbons. That would probably give you some different options. You could even do ones like this. Let's get crazy with the rings here. Okay, where they're connected in the middle and connected down here. Holy cow, now fill it out. 1, 2, 3, 4, 5, 6. There's another one, okay? So we could go on and on with this, but you could do a ring structure where there's a double bond outside of the ring. What's the matter with that? That's legal. So there's 2, 3, 4, 5, 6. There's another one, and so on and so forth. But you get the gist of this. You get the gist of this. Some of them, you can go, like I was saying, there's 28 or there's 35 or there's 110 or there's 1,000 of them. And as you can imagine, you add carbons and hydrogens, you can really go on and on for this. Okay, if you're feeling like a real animal, pause the video and see how many isomers of C5H8 you can draw. Go. Okay, I've popped a few down here, but I mean, you can really go crazy. Apparently there's 28 different ones, okay? But I've put how many here? 1, 2, 3, 4, 5, 6, 7. So you see that one, 7. I've got the 5-member ring. Here, I'll highlight what I'm talking about as I'm doing it. I've got the 5-member ring in that one. I got a 4-member ring in that one, and a 3-member ring. And there are many, many variations on each of these ring structures, and you change around where the methyl branches are, and you can do all sorts of stuff. I also just wanted to show a couple things, like this one is actually the cis form of whatever this one would be called. You could name it at your leisure, but that would be the cis form of it, wouldn't it? And then over here, this one would actually be the trans form of it. Okay, so the fact that cis and trans exist as well, anytime there's a double bond, this all counts as a big group bonded to it, right? And then you compare it to the heavier group on the other side, and you've got cis and trans. So you could really go to town with this. There's just one other little thing I want to show you on the next slide. And what I want to show you is just to be a little bit careful. If you look at the isomers of something like C5H12, you want to be careful in saying, like, okay, clearly this is one isomer, it's pentane. By the way, of course, most of these are going to be alkanes. It's on CnH2n plus 2 general formula, isn't it? So we've got your basic pentane, and then you might say, okay, hey, here's another one. I got a wise idea. We can just put one like that. Is that cool? Right? Is that a different structure? No, it's not. All you did was rotate this thing that way. That's not a different structure. That's the exact same structure. Okay, that's not a new one. Or then you might say, okay, I get it. You got to change the bonding up a little bit. So I'm going to put 4 in a row and put one there. Okay, cool. So I got one like this. And, I got another idea. I'll put one up here and one up there. Okay, 1, 2, 3, 4, 5. All right, are those different structures? Well, no. You just, instead of positioning it in kind of a T format, you've drawn it like a Y, but it's really the exact same structure, isn't it? So it's not a new one. So you have to think in 3 dimensions a little bit and realize that we're making a 2-dimensional model of a 3-dimensional thing. And so sometimes, particularly with the structural isomers, you may get fooled into thinking it's something completely different when it's not. So do be a little bit careful with these. They can be tricky. Anyway, I hope this helps you understand isomers and you have a little fun trying to come up with all the structures.